Welcome to this explainer. Today, we're going to dive deep and uncover the fascinating hidden science behind how farmed salmon are raised. We're essentially transforming a dry biology lesson into this absolutely incredible story of environmental engineering. We'll be exploring all those invisible variables that farmers have to master to turn a tiny, fragile egg into a thriving adult fish. We've got 5 main stops on our journey today: meeting the young salmon, the great saltwater shift, managing tank density, the oxygen equation, and finally, perfecting the feeding regime. Let's jump right in. Part 1. Meeting the young salmon and their biological journey. Okay, so a salmon goes through these fundamental, chronological life stages. They start out as a tiny yolk sac fry, where they are entirely dependent on their attached yolk for nutrients. Then comes the absolutely critical first feeding stage, where they transition to external food. Once they pass that hurdle, we call them fry. As they continue to grow and develop, they become Parr, and finally, they hit the smolt stage, which basically means they are fully ready for saltwater. And you can actually see this visual evolution perfectly right here. We start with the pale fry on the left, but as they grow into that Parr stage on the right, notice how they develop rounder bodies and those dark vertical bars. In the wild, those Parr marks are like a magic trick. They act as perfect river camouflage, helping these young fish blend seamlessly into the rocky, dappled light of a stream bed. Moving on to step 2, the great saltwater shift and preparing for the ocean. That massive transformation we just touched on, it's called smoltification. And honestly, smoltification is a huge biological hurdle. Think about it for a second. Only a handful of species on the entire planet are actually capable of surviving such a drastic change in salinity. It's not just a matter of swimming downstream into the ocean. It requires a complete overhaul. We're talking changes in their appearance, their internal structure, and entirely new ways for their bodies to function just to handle the salt. Now here's where it gets really fascinating. Look at how farming completely alters the timeline of this process. Under natural conditions, a wild Atlantic salmon might take anywhere from 2 to 7 long years to reach a weight of just 20 to 30 grams before it's ready for this saltwater shift. But, time is literally money in aquaculture. The industry needs much larger smolts to ensure high survival rates out in the sea pens. So, under optimized farmed conditions, they're pushing these fish to reach 50 to 100 grams before they even undergo smoltification. Which brings us to part 3. Managing tank density, the environmental pivot. So the first major invisible variable farmers have to manipulate is space, and the math actually changes as the fish age. On the left, during the start feeding phase, the fry stay entirely on the bottom of the tank. Because of that, farmers calculate space purely by surface area. But once they grow into Parr, like on the right, they start swimming upward and utilizing the entire water column. The exact moment that happens, the farmer's math has to shift. They now calculate fish density per cubic meter. So, how many fish can you actually fit into that cubic meter? Well, experimental conditions have successfully pushed densities way up to several hundred fish without immediate harm. But actually, commercial farmers play it much smarter. They generally set a strict upper limit of 60 to 80 kilograms of fish per cubic meter. Staying within this limit is absolutely crucial because it ensures they avoid detrimental effects on growth and maintains a healthy, stress-free environment for the salmon. Next up, part 4, the oxygen equation, the ultimate invisible variable. To really wrap your head around what low oxygen feels like for a fish, imagine sitting down and eating a hamburger while resting quietly. Easy, no problem, right? Now imagine trying to eat that exact same burger while gasping for air after sprinting a full kilometer. You couldn't do it. You'd be way too focused on just trying to catch your breath. That is exactly what happens to a salmon at suboptimal oxygen levels. If oxygen is low, the fish simply cannot consume or digest the feed they desperately need to grow. Because of this, farmers have a golden rule to ensure the salmon can actually process their food and grow rapidly. They have to carefully manage the water flow to maintain a minimum limit of 80% oxygen saturation at the tank's outlet. If the water leaving the tank is at 80%, they know for sure that the fish inside have plenty of oxygen to eat comfortably. But take a look at this. Farmers are up against a really complex chemical reality here. Notice how these numbers drop. Oxygen solubility isn't just a constant. It drops drastically depending on both the temperature and the salinity of the water. Basically, warm, salty water holds significantly less oxygen than cold, fresh water.
And this creates just a wildly high-stakes balancing act for the farmers. Because fish are cold-blooded, their body temperature naturally matches the water. So as the water gets warmer, it physically holds less oxygen. But simultaneously, and here's the kicker, that same warm water causes the fish's metabolism to spike, meaning they suddenly need even more oxygen to survive. Add to that the fact that smaller fish consume way more oxygen per kilogram than larger fish, and it's easy to see why farmers must constantly monitor and adjust to these invisible variables.
Finally, let's look at part 5, perfecting the feeding regime, the actual business of growth. So once the environment is locked in perfectly, how do we maximize growth? Automated disc feeders. These are absolutely vital to modern aquaculture. They don't just dump a pile of food into the water, they disperse the feed widely across the entire surface. This is critical because it ensures all the fish can feed without having to aggressively struggle or fight each other for a bite. By removing that struggle, the fish save a ton of energy, reserving it purely for growing. But you can't just feed them all at once. Remember our biology lesson from earlier? Smaller fish naturally have much smaller stomachs. Therefore, these computer-controlled feeding regimes have to be incredibly precise. The systems are programmed to distribute much smaller rations constantly over a 24-hour period. This perfectly accommodates the tiny, quickly emptying stomachs of the young salmon. Which leaves us with a pretty fascinating realization. Figuring out the daily feed for thousands of exponentially growing fish is insanely complex. I mean, their weight changes literally every single day. So to manage this, farmers actually program their computers using the exact same compound interest formula that you use to calculate the growth of your money in a bank account. It perfectly proves that the business of aquaculture isn't just farming. It's a continuous, carefully calculated investment in life. And that brings us to a profound question. As we continue to push the boundaries of biological engineering and automation to feed a rapidly growing planet, where will the math take us next?